Hi, Miss Danny. Okay. Yes.
I think I know that person.
I think you know that person. That person. Yeah. We know that person. Hello, Kai.
Hello. Yeah, I'm not muted. Okay.
Absolutely no approach. We're probably gonna like once his screen's here, they won't be able to see us. But, like,
No, you'll still be able to see you. The screen share comes from this computer. That's the whole room. It's been like that every week.
but on the video, like you just see the thing.
Why is
Yeah.
Hi? Why do you cook every week? You're always cooking something. Weird. Like
Well, because I'm babysitting every week. Except for next week, I will be in class next week. So holla. But yeah,
Yay!
I know I'm excited. I'm making cupcakes and lunch. So
cupcakes and lunch. Cool. Is that eggs last week?
It doesn't matter.
Just eggs.
Yeah. All right. Let's see who's missing. Shannon's not here yet.
No, I'm gonna shove this up his nose.
Did she send you?
That's such a smart idea.
I'm just trying to see if Shannon sent me a.
So when I come to
I'm just using Lily's account, so I'm here, by the way.
Hey, Ethan.
No, you're just the one holding him down. I'm just gonna be the one like.
Okay. I'm eating my lunch over here, so. All right, so the last two chapters have had a lot in them. I will be the first to say a lot. And some of it was probably overwhelming, like, good gracious, how in the world are we ever gonna learn all this stuff? So what I did is I spent a lot of time over the last couple days trying to break it down for you guys to what it is I actually want you to know versus everything. Now, I did find, strangely enough, online, I happened upon a slideshow for this lesson, essentially this chapter 6 in your book, that came from like the teacher resources for the book, like a school system had bought that. And so I put that slideshow, I'm a screen share. I put that slideshow in the folder for your class. So, and I linked it if you want to see it, but basically it's, it has all the things. It's taking this chapter and it's super detailed. Alex, that's bizarre. So anyway, it looks like this and it's super duper involved. And I spent a lot of time trying to make it cleaner, better, animated, all this stuff. But I mean, there, how many slides were there? No joke, 100 and something, 85 slides. And I spent like 6 or 7 hours on it. And then I was like, I don't like this. So I did something separate for you all that's smaller, more condensed, not so crazy. So anyway, this is there if you want to look over it. It has all the good information in it. But the one that I want you guys to focus on is the one we're going to go over today, because it should cover everything that I want you to know, because there's a ton to know. You could go on and on with this stuff forever. So what I want you to know is the stuff that I put in this slideshow, which is, hang on, I'll tell you how many slides. Nowhere near as many, 25. And that includes your homework pages in here. So I whittled it down to the basics. Yes, okay. You're fine. This is probably my YouTube videos that it doesn't like. All right, so last week we talked a lot about ionic bonding. This week is covalent bonding, right? We have three main types of bonds. We've got ionic bonds, covalent bonds, and metallic bonds, right? There's also hydrogen bonds. Well, we're not messing with them right now. So are y'all obsessed? Like, do we need to do something? Y'all are insane. Okay, so chemical bonds. This is your definition. Now, if I were you, what I would do today is I would get a pencil and I would write some notes somewhere along the pages in your binder or circle the stuff that's in your binder that comes up today, because this is the big stuff. So the definition of a chemical bond is the attractive force that holds atoms or ions together. Covers all the different kinds of bonds, right? So you're going to want to understand the definition of a chemical bond. And then we have our three main types of chemical bonds. So we were just talking about this one, ionic, covalent, and there are two types of covalent, and metallic. There are three main types, not three only types, three main types. What are our two types of covalent bonds? Not a girl, polar, non-polar. Okay. So make sure everybody has a chance to write or whatever you're doing. And this is, you can go back and look at this. It's totally there for you. All right, so here are the ionic bonding and ionic compounds, which is what we went over last week. So here's your review of this. So this one's simple. It's not as involved as the covalent one. So you have an ionic compound, which is a compound composed of ions bound together by electrostatic attraction. That's your positive and your negative, right? That should have gone the other way. Wow, I did those backwards. Look at that. Hold on, that's so stupid. Those are supposed to be disappear, not appear. Hold up. I hope all the others aren't messed up like that, because that's going to make me mad. Go out of the way. Oh man, I can't see it. Come on, there we go. See, look at that. They're supposed to disappear. I'm making that better. Because y'all, I'm out of it. Oh, there we go. So back to where we were. Don't mind me. So there we are. Did it go the whole other way around? It probably did. Oh man, look at this. There we go. All right, I give up. Formula unit. So remember that we don't call collections of atoms corresponding to ionic compound formula. When it comes to, we don't call them molecules, right? We call them formula units. So the definition of a formula unit is a collection of atoms corresponding to an ionic compound's formula. And then it goes on such that the molar mass of the compound is the same as one mass. We don't need that. What you need to know is that your ionic compound, your formula unit is basically one of your ionic compound, not a molecule, because molecules are, we use that for molecular bonding, which is covalency, not ionic, right? And then we have polyatomic ion, which is exactly what it sounds like, an ion made of two or more atoms. Uh-huh.
Is this going to be an email that you send with
The link is already in Teacher Ease. I mean, not the link. Well, yes. If you go to Teacher Ease, which I can't open because it shows everybody's grades, but if you go to Teacher Ease and go to today's lesson, like class participation, this is there.
on the app or on the website?
It's on the app, the Teacher Ease app.
The
Well,
app
either way.
works so well. Okay.
The app is harder to use, like on your phone.
My app doesn't work. It doesn't work.
The website's way better. I have a hard time with the app too. It's really not meant for teachers, for daggone sure. It's really more like showing you what to do. That's about all it does, but it doesn't let you.
Create accounts is what happens, so I can
Yeah.
only do it if like a notification comes in.
Right.
Like that.
So ionic bonds are always forming between a metal and a non-metal. And you're talking about complete transfer of electrons, so stealing or donating, not sharing. Sharing goes with covalence, right? Right. And then they form ions. Duh, we get that. Remember that they're solid at room temperature. Do you guys remember the characteristics of ionic compounds? Solid at room temperature. Crystal, yep. Brittle, right? And what else? High melting points. Yep, there you go. High melting points, strong bonds, right? Brittle. And non-conductive, but except when they're in a liquid form or in a solution. Like if you had molten salt, super conductive, but that's going to be really hard to get. Right. Full ionic charges. All right, ionic bonding. Force that attracts electrons from one atom to another, which transforms a neutral atom into an ion. And if you remember, when you're dealing with ionic bonding, your compounds make these nice, neat little lattices like that. Remember we talked about like a Lego structure? Super tight. Three-dimensional network of positive and negative ions, mutually attracted to one another. This is all just review because we did this last week. Hard and brittle, higher melting points, boiling points, right? That's what we just said. All right, now we get into newer stuff. I don't know what is up with my animations, man. I'm about to give up on this. Okay, this is what happens when you spend 7 hours on one slideshow and then like 3 on the next one, you start to lose your mind. So the first thing, you don't, I wouldn't write down all the definition, there's not room, but you could write down the terms so that you remember to look them up. So covalent bonds produce molecules, groups of atoms that are held together by chemical forces. A molecule is the smallest unit of matter that can exist by itself and retain all of the substance's chemical properties. So an element is going to maintain all of the properties of, he's out, all the properties of that particular element. But then if you have, it should be unlocked. But then if you have a substance, the smallest unit of that substance, if it's covalently bonded.
He's trying to get out with this, so he's just walking into the.
Oh, well, that isn't gonna work. He can't, that won't fit through the door.
I think he's so smart. And then
Yeah, then he does dog things. Yeah. So if you're talking about smallest unit of a substance that's not an ionic substance, it's going to be the molecule. Wow, that's way out of order. Okay, molecular compound, that's the substance we're speaking of. So you're talking about a chemical compound whose simplest units are molecules. So those two definitions play off one another, right? Can't have one without the other. And then you have a chemical formula. So your chemical formula is your combination of chemical symbols and numbers that represent a substance. You guys know that, like C6H12O6 or H2O, any of these ones that we use frequently. NaCl is an ionic one, but it's still a chemical formula. Oh, look, it's so backwards. Okay, molecular formula is a chemical formula that shows the number and kinds of atoms in a molecule, but not the arrangement. Okay, so you guys read in this chapter that the bonds within a molecule cause a certain shape and a certain arrangement to occur. Like some of them are bent, some of them form pyramidal type shapes, and it all has to do with what types of bonds are there. And I found a really great video of this dude who, like, he has this little trick to help you remember. But if we're being honest, I don't expect you to memorize all of that. That's not an essential thing for you to memorize. The concept is more important. It's more important for you to get the concept of why things are the way they are than to be able to rattle off all the information. Because you can look, it's ubiquitous, it's on your phone. You can look it up in 2 seconds. Why? That's not where your mental energy should be going. So when we talk about molecular formulas, it's written out like a chemical formula, but it doesn't necessarily show you how it's arranged. And then, oh, good, finally, an electron configuration notation in which only the valence electrons of an atom of a particular element are shown, indicated by dots placed around the element symbol. What's that? Do you know what it is? Yeah, that's it. That's your Lewis dot or Lewis structure. And oh, it's just, look at this. It's like, why is this not showing up? Okay, hold on. I'm gonna try and fix that because that's ridiculous. I don't know why it's so out of whack. So that's the electron dot notation. The Lewis structure is the one that follows that. So that's your structural formula. Hold on 1 second. Let me see if I can make them do what they're supposed to do, because they're being dumb right now. And it makes me crazy because I'm very picky about slideshows. So I'm annoyed when they don't work right. Oopsie, get out of my way. You what? What?
Has the COVID ever got like, get sick of COVID like through your eyes? You just.
Okay, maybe that'll work now. Okay.
we all just need to
So your
close our
electron
eyes.
dot structure is the one we were talking about before. Come on, come on, come on, come on, come on, come on. There we go. So here we go. So this one is where we're looking for your Lewis dot structural formula in which electrons are represented by dots or pairs or dashes between the symbols that represent pairs in covalent bonds. So this next one, structural formula, a formula that indicates a location of atoms. This is still wrong, so I just give up. Oh God, the location of atoms, groups, ions relative to one another in a molecule, and indicates that the number and location of chemical bonds. And then you have single bond. Okay, single bond is when you have 2 atoms sharing one pair. That's the trick, is pair. You have to remember pair. So when you're dealing with single bond, double bond, and triple bond, it's about pairs.
Yeah.
So a single bond is 2 electrons.
2, 4, 6.
Right, 2, 4, and 6. Now this just notes also multiple bond, right, which is
But
a bond in
goes
which
higher than triple bond, right? Because I remember looking something up.
you
like
could
that.
do
There's like
multiple
4,
bond, yeah.
5.
But we're focusing mainly on single, double, and triple. So when you're doing single, double, and triple, it's pairs. And that's what gets tricky. You have to remember pairs. And then resonance is the idea that bonding in molecules or ions that cannot be, that you can't correctly represent the structure at any time because of the way things are moving. And I have found an interesting video on that, actually, that I'll show you in a second. So covalent bonding is between your non-metal and your non-metal. So ionic bonding is between a what? A metal and a non-metal. Covalent bonding is between a non-metal and a non-metal. So the only other option is metal and metal, and those are metallic bonds, right? Obviously, we are good. All right. Covalent bonding shares electrons, right? We're sharing. We're being nice. We're not stealing. Ions are stealing. Molecules, not formula units. Yep. Oh, yeah. Solid, liquid, gas at room temperature that can be any of the above. Okay. And low melting points and low boiling points, which we saw today, didn't we?
That's a fun map.
Literally things on fire.
Those of you that are normally here that aren't here today, like Kai and Lil, it says Lil, Ethan, go and go to the lab on Teacher Ease, and Shannon should be here too. I don't know where she is. Go to the lab on Teacher Ease and you can pull up the video. There's a video for today's lab I already did, so you can watch that. Ooh, delicious Kai's cupcakes. And they can be brittle, they can be bendy, they can be different. Soluble in water, poor conductors. And then I skipped that because I clicked one too many times. Polar and non-polar. Okay, so polar is when you've got unequal sharing. We're sharing electrons. So polar is if you're not sharing them equally. It's like a tug of war, okay? So picture John Cena on one side, okay? And then picture, who should we put on the other side?
Somebody small.
Who?
Godzilla.
Somebody smaller than John Cena.
Danny DeVito.
All right. So John
I'm
Cena
not wrong.
and Danny DeVito are sharing a pizza. Who's gonna get more of the pizza?
Well, are they fighting over it?
Yeah, if they were fighting over it,
To the death.
or who's more likely to eat more of that pizza? That's gonna be John Cena, right? He's gonna kind of pull more pizza in his direction. It's sort of like you and your friend have 3 cookies. One of you is gonna, Shannon. One of
Yeah,
you is
you're
gonna
get
eat.
one, and then your friend's gonna say break it in half. So you're like, cool, if you break it in half.
No, he's just gonna get 2. You're gonna get 1 and your friend's gonna get 2. That's your polar. You're sharing those 3 cookies. Those 3 cookies still exist, but he's getting more of them than you. Because whatever, he's stronger. He wants the cookies more. Non-polar would be if you had 4 cookies and you each had 2. You can't say 3 because you can't split an electron like that. But it's 2. And non-polar always occurs if you have 2 identical nonmetals, then it's always going to be non-polar. And you can get polar when you have 2 different nonmetals. Okay. All right. So covalent bonding occurs when atoms share 1 or more pairs of electrons. Non-polar covalent bond occurs when electrons are equally attracted, and a polar covalent bond is when the electrons are going to be attracted more closely by one of the atoms. So atoms and molecules are joined by covalent bonds. In covalent bond, 2 atoms share 1 or more pairs of electrons. The octet rule states that many chemical compounds tend to form bonds so that each atom shares or has 8 electrons in the highest occupied level. We know that, right? And bonding with many molecules and ions can be indicated by a Lewis structure. Molecules or ions that cannot be correctly represented by a single Lewis structure are represented by atoms. Okay, so let's hope this works and pulls up this. Where's the dude's video? Oh, I know where it is. It's in the other thing.
We're learning about metallic bonding.
Metallic. Okay, so metallic bonding.
Oh, I don't like that one.
So now we're in the other of the 3. Okay, finally finished eating. So for metallic bonding, there's a lot of these characteristics. Metallic bonding produces substances that are malleable.
Soft,
So
slippery,
malleable,
solid,
yeah.
conductive.
Hang on, malleable means what?
Not necessarily breakable, but you can manipulate it.
Yeah, it can be
Move
hammered or
around,
beaten
hammered,
or
beaten.
twisted or bent or whatever into a shape. That's malleable. They also are ductile. So ductility means you can hammer it or draw it into a thin wire. So think about copper. Copper is a great example because copper is very malleable and it can be drawn into a nice thin wire. If metal wasn't ductile, we couldn't use it as efficiently as we do in cords and cables and things like that.
Those wires, don't they just take copper and they,
Draw it out,
and they get it to the point where it's melting enough that you can do something with it and then just stretch it?
start pulling. Yep. Mhm.
I'm doing like easy ways to remember, like ductility is quack. and
Quack.
Theirs is I love that fruit. So.
All
just
right.
so, like,
There we go. Whatever works for your brain, man. And then
it
the
doesn't work, so-
metals are highly conductive. Okay, so when you think about, remember when we talked about the way ionic substances are structured? They're put together like almost like the Legos, right? They're interlocked, they're nice, and they all fit together.
They're
So
holding each other.
the same kind of thing happens in a metallic bond, except the electrons are not locked. They flow all around. So the electron that's with one atom might switch off to another one, almost like some sort of continuous loop. And they call it the sea of electrons. And that's exactly why they're so conductive, especially for electrical energy, because you're just moving the charge. It's basically just continuing to move the electrons, right? You've got this big squishy sea of electrons and they just go wherever they need to go. That doesn't happen in other substances where the electrons are kind of locked into the structure. So that's why metals are different. They allow for all this free flowing electrons. So here's a great picture. In a metallic bond is formed by the attraction between positively charged metal ions and electrons around them. So here are your metal ions, because that's typically how they're gonna exist, right? They don't exist, those metals don't go around with the octet rule filled, right? They're somewhere in the middle of the table. So if they're in the middle of the table, they don't have a noble gas configuration. So they're going to be an ion. And there they are needing these electrons. So these electrons just bounce all around in between all of them, keeping the entire structure neutral, if that makes sense. So there's the electron C is formed in metallic bonding, gives metals their properties of high electrical and thermal conductivity, malleability, ductility, and luster. That all of these properties that we think of as indicative of metals come from the fact that they have these free-flowing electrons. So other types of bonds: ionic bond, covalent bond, metallic bond, James bond, hydrogen bonding. And that's an intermolecular force occurring when a hydrogen atom that is bonded to a highly electronegative atom of one molecule is attracted to two unshared electrons. We're not worrying about it much. Just know that it's a thing, okay? It's not a thing we're doing today, but it's a thing. Dude, Ozzy. I need to zap him.
I think the most important type of bond is James.
James bond is a great type of bond, I would agree.
Leave it us.
So here's some other terms you should know, okay? Shush, Ozzy. Bond energy. So bond energy is the energy required to break the bond in 1 mole of a chemical compound. Not energy to form it. When they form it, it doesn't require energy, it's releasing energy. So in this case, if you're going to break the bond, you need to have a certain amount of energy, and we call that bond energy. Lattice energy is associated with constructing crystal lattice relative to all the energy of all the atoms. Just this one isn't as important. Just know it's a thing too, okay? Now, dipoles. All right. So dipoles are molecules where a part of the molecule contains both positive and negative charge regions. So there are some molecules that are dipoles. Are nonpolar molecules going to be dipoles? Are nonpolar molecules going to be dipoles? No. No, it's not going to happen. So now there's this. They do say this as Vesper theory. That's often how it's said, although that's kind of weird because you think that E would go first, but it doesn't. But they do say Vesper theory. All right, so here's,
The separate.
yeah, the Vesper. This is how you predict the shape of the molecules. So I don't want you to memorize this, but I want you to know what it is and how it works, okay? So VSEPR theory predicts some molecular shapes based on the idea that pairs of valence electrons surrounding an atom repel each other. So this is a chart that shows you exactly how all of it works. So it'll tell you here, for example, here's a generic formula, element A and element X, 3 of them. And it shows you how they will be set up, how many bonded pairs there are, okay? And I'll show you the video of the guy that does the great job narrowing it down, because he really did. He did like a little, it's almost like a mnemonic device. I'd never seen it done, but it was really cool. So it says, note there are no lone pairs or X or other atoms, but we don't care. We're interested only in the electron densities or domains around atom A. So A is where the focus is for every one of these. But this is an example right here. So it says AX to E. So if you look here, this is bent and this is bent. So water molecules, all right? If you've ever seen a diagram of a water molecule, you've got your oxygen and then your 2 hydrogens, and it's kind of this shaped. So it's bent. And that's because there is a certain amount of repulsion where the protons are concerned. And then there's a certain amount of repulsion where the electrons are concerned. And then there's attraction involved too. So your 2 hydrogens are getting pulled, right, towards that center, that the electrons and the hydrogens are pulling all towards the larger number of protons in the oxygen. So they're coming in like this, but they can only go but so far in, so they try and kind of wrap around. Well, as they wrap around, they run into each other. And when they run into each other, they're repelling because they've got the negatives going on the outside of the valence. So that's how you get this bent shape. And that happens with all molecules. So here's the dude with the shortcut. Let's see if it works, because I don't want to have to go to YouTube for it, but okay, it's going to work. Excellent.
Hey, here we talk about chemical bonding. In that, we take VSEPR theory.
Can I make it bigger?
And I know you're not able to learn some shapes of the molecules if you're given about the lone pairs and the bond pairs. But I now have a very interesting way that you can learn them.
Where can't I see him?
Yes, you will not
Jeez.
forget them. See, what you have to do is
Okay, hold on.
make a table like this, 21, 20.
Hold on. You can't see him. Why can't I get down there? This is not, oh my gracious, why is this thing being
Hey, here we
stupid?
talk about chemical
Hold on,
bonding.
dude, wait.
In that,
What are you trying to do?
I'm trying to get it back to here. So maybe you can see it better because it's half of it's out of the screen. I was telling you, I had issues this week. Okay, play. There we go.
Hey, here we talk about chemical bonding. In that, we take VSEPR theory here.
Hello. There he goes.
Hey, here we talk about chemical bonding. In that, we take VSEPR theory here. And I know you're not able to learn some shapes of the molecules if you're given about the lone pairs and the bond pairs. But I now have a very interesting way that you can learn them very easily. Yes, you will not forget them. See, what you have to do is
You will not forget them.
make a table like this, 21, 22, 31, 32, 41, 42, and 51. Now, separate them. These are bond pairs, these are lone pairs, and here we have the shapes. Bent, bent, trigonal pyramidal, T-shape, seesaw,
Seesaw.
square planar, and square pyramidal.
What's the second one? Square what?
Square
If you
planar
learn
and
about
square
them-
pyramidal.
The way I want you to, then you will not forget. Yes.
Not forget.
T comes before everything alphabetically, but you'll say T comes after S, but you just remember beats.
Beats.
So T everyone with an S
Like
and
the
last.
alpha.
Okay.
Mm-hmm.
Now see, for remembering which one comes before in T pyramidal and T shape, go alphabetically. Here we have the P, and here is S. Which comes before? Simply P. And in these three, you can learn it like at 41 Street, she saw me.
I love that.
We had 42 square planar and 51 square planar group. And if you look which one comes before in these two, then you can see here we have L is alphabetically before.
That's ingenious. Like if you were doing college level chemistry and you needed all that memorized, that's ingenious. I like the dude.
I also have a rhyme for you. Band, T pyramidal, T shape, C saw me at 41 Street. We made 42
He's
square
gonna sing.
planar and 51 square pyramidals. Nina like
That's fine.
do not just skip it. Do not. All right.
Don't skip it.
Learn.
Don't skip it. Learn it. I like him. He's cool. I thought that was really interesting. I'd never seen anybody do that. I was like, hey, dude, that's pretty awesome.
That guy probably freestyles great.
So this is a review of last week. We talked about how to find the ionic charge of transition metals. Okay, now I put this video in the email, but I don't know if everybody saw it. So we were trying to figure out like, what do we do with these Roman numerals and stuff, right? Okay, so this is how that works. We're gonna follow up by trying to get a few of them ourselves.
About how to find the ionic charge for transition.
I'm surprised I haven't gotten a million political ads in front
I
of me.
watched the guy.
Look for ionic charge. We often think of
This is very helpful.
Hey,
I
Mhm.
watched this video, but I know what this guy's on.
1 plus ion.
Ooh, I need to go grab the
2
table real quick.
plus, and we
You're right.
skip the transition.
Why isn't he
That's
reading
what
the
we're
audio?
interested about. This thing. We skip them and we go 3 plus, 4 plus or minus, and 3 minus 2 minus 1 minus 0. And that's very useful to understand the general trend for ionic charge on the periodic table. It's a bit of an oversimplification though. If we look at a more detailed periodic table, we see that we still have group 1, they're all 1 plus, 2 is 2 plus. So here are the transition metals. We have these post-transition metals, some of these things here like that. So this is more detailed, and you'll note that there's really no 4 plus or 4 minus on this table. So here we have 3 transition metals though, that always have the same ionic charge. Silver, 1 plus, and then zinc and cadmium, they're always 2 plus. But for the rest of them, some of these transition metal families, we really don't know what the ionic charge is. To find it, we'll look and see what it's bonded to. So these are all positive. We'll see what they bond to here, and then we can work backwards to determine the ionic charge. Let's try that, see how it looks. Let's try copper oxide. So copper transition metals right around here. We don't know its charge, but oxygen, you know that oxygen right here is a 2 minus ionic charge. And this copper oxide right now, it's neutral. There's no plus or minus out here. So all the charges, they add up to 0. The net charge is 0. Oxygen, 2 minus. That means for them all to add up to 0, the copper has to be 2 plus. And that's its ionic charge. We would say for the name, copper 2 oxide. And the 2 would be a Roman numeral in parentheses after the word copper. So copper 2 oxide here. Let's try another one, maybe a little more complicated. How about Fe2O3? This is a conforming rough. So we don't know what iron is, it's a chemical, but we do know again that oxygen.
It's not gonna get you on this, wait.
And we know that all the charges on the Fe2O3 compound, they have to add up to 0. So 3 times 2 minus, that's 6 minus. So this part of the compound is 6 minus. The question is, to get 6 plus, what is the charge on the ion?
So what do you have to do? You have 2 of them.
2 times something will give us 6 plus.
So it's,
2
yes,
times
3.
3 plus. That'll give us 6 plus. These will cancel out, they'll add up to 0. So the ionic charge on the iron is 3 plus. We call this iron
3.
oxide. And note that this 3 plus, there's 2 iron atoms, so each one is 3 plus. Now you try this. How about CuCl2?
All right. What do you think? You got a -1 on the chlorine.
CuCl2, again, copper, that's a
Yeah.
transition metal right around here. Chlorine, that's right here. In group 17, sometimes called 7A. All of these have the 1 minus ionic charge. Right, 1 minus right here. 2 times 1 minus, that's 2 minus. So the copper have this 2 plus, so these add up to 0. Has to be 2 plus. Kind of imagine a 1 times 2 plus.
Yeah.
The 2 plus. Net charge is 0. The charge on copper is 2 plus. We call it copper.
Copper 2 chloride.
Chloride. Pause and try this one.
All right, I'm literally gonna pause. Okay. Look for sulfur. I got this one up so you can see it. -2.
So can you close the thingy?
Yeah.
Sulfur is over here, so that's gonna be a 2 minus,
Yeah, 2 minus.
and then iron is somewhere.
Iron's in the
And
middle.
so six.
Iron's negative is positive 3.
Positive 3.
Okay.
I was gonna say it before you did, but you beat me.
So for Fe2S3, it's pretty much the same as Fe2O3 because these are in the same group. Overall, neutral compound. So we look up oxygen right there. 2 minus, 3 times 2 minus.
6.
This has to be 6 plus.
So how do you
2
do it?
times 3 plus. That'll give us 6
Boom.
plus. Net charge is
See,
0.
you got it.
Iron 3 sulfur. We'll wrap up with one more.
Okay.
ZnCl2.
Okay. ZnCl2.
Which means it's plus 2.
There you go. Look at that. See, there was one like this on the test and not everybody got it, but I didn't feel like we had gone over it enough last week.
That makes sense.
There you go. There you go. Well, you have to do it again and again and again. So when I looked back at the test and I was like, you know what? I'm not going to count it against anybody because I don't think we went over it enough.
For the first time, it's
Now it's making more
because
sense.
it's like not at the end of class, so.
Like, just like this.
Yeah, we're going to actually do a little bit like that in a minute. But there's also
So again,
in
neutral
that
compound, all the charges
email,
add up to
there's
0.
links for flashcards and sites that do that. They just roll them at you. You can just do it and do it and do it.
2 of them. So 2 minus the zinc has to be 2 plus.
There you go.
We also know zinc is an exception for the transition metals. It's always 2 plus. So we could have known that without figuring out this morning. If we name this compound, because zinc is always 2 plus, we can just call it zinc chloride. We don't have to call it zinc 2 chloride.
It's not wrong to call it zinc 2 chloride.
This is Dr. B with the ionic charges
Thank
for
you.
transition metals.
So I like that. That's great. That's really good. Good stuff. All right, so now we have naming covalent compounds, which is a little different. I don't think it's as hard though. I think that naming ionic compounds is harder.
Welcome to Math and Science. In this video, I'd like to talk about writing covalent compound formulas. Covalent compounds are composed of 2 metals. You can find the nonmetals on the right side of the periodic table. Covalent compound formulas use prefixes. The prefixes go like this. Mono is 1, di is 2,
Tri,
Tri
tetra,
is
penta, hexa.
tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona 9, and deca 10. It will help you if you memorize these.
Those are worth memorizing.
Let's get
Those aren't hard
started
anyway.
with a couple of formulas, and I'll go through some of the rules.
Those are
Up
Greek
first
as
is
opposed to Latin.
CO. Rule number 1, with the first element, if it does not have more than 1, or in other words, if it's just 1, you just say the element. You don't say monocarbon.
Just
And
carbon.
then for the second one, you do add the prefix. So this will be carbon monoxide. Up next.
Now
is
note there that
N2O.
if you've
Now
got
we have two
another
nitrogens.
O, it's not monooxide, right? It's just monoxide. You drop that one O, which is pretty obvious, I think, but
And so we will use a prefix of di. So it will be dinitrogen monoxide.
see, this is easier,
because
isn't
you
it?
only have
There's
one
not as much
oxygen.
math.
Also notice that instead of all of oxygen for the second term,
Good.
you use I-D-E.
Mm-hmm.
Next, you have N2O3. So let's put all the rules together.
You have dinitrogen
Dinitrogen.
because you have 2 nitrogens. And then you have 3 oxygens, so it will be tri.
Trioxide.
And then you add the IDE, so it'd be trioxide, dinitrogen trioxide. Now let's work it the other way. Up first, we have SO2. That will be sulfur because you only have one of those. And it's the element name, so it'll be sulfur. Then you have 2 oxygens, it'll be
Dioxide.
dioxide.
Makes sense.
Next, you have pH3, and that will be phosphorus trihydride. And finally,
Hydride.
you have
The hydrogen
CH4, which is
Go
carbon
away.
tetrahydride. So there we go, naming covalent formulas.
So that makes sense,
Thanks for
right?
watching and move.
All right, so here we go. Now we're gonna try. So we have hydrogen peroxide at the top, and that one is an example. You can see that. And they don't say dihydrogen because it's always going to be with a buddy because it only has the one. And that's a common thing, hydrogen peroxide. It wouldn't be wrong to say dihydrogen. A good point. That has to do, wait a minute. Oh, that might be, no, that's right. It is because, wait a minute. I need to look that one up. I didn't even notice that. No, you're right. It would be, but it's not.
What's
Per is the 4.
No, tetra is 4.
No, tetra's 4. Oh, wait, that's what the per is. It has to do with it. I'll look that one up while you guys go into the next one, because now I don't. Well, anyway, there's a per here too. So there.
Sodium 2 bar.
Oh, there's an 8 too. Some of these are 8s, and we haven't gotten to 8s yet. So this one here, let's see. Some of these might not be totally ready yet. So don't worry about the 10H2O. That's just saying it's aqueous. But Na2B4O7. So what would you say? 2 sodium would be so because it has an oxygen, this is one thing it didn't go over yet. All these were ides and ides and ides, but if you have an oxygen, you get 8. So if there's an oxygen in it, tetraborate, right? And then this is, because this is borate, you combine this and this. So when you see the B and the O together, this becomes a borate. And this becomes this is a tetraborate. You just stick them together. And then this, the decahydrate. Okay. Okay, so this next one's easy. What's
Sulfur.
Yeah, sulfur. That's easy.
Which is another ingredient.
Okay, this one we don't know the tartrate yet, but can you figure what the beginning of it would be? K and H. And this part they call tartrate, which is kind of ridiculous. The C4H4O6. All right, Epsom salt. How about this one? You can probably do this one. It's an SO4, so it's going to be a what? Just like all these.
Sulfate.
Yeah, it's going to be a sulfate. Sulfate. Septahydrate. Yeah, or heptahydrate. My fault. Okay, how about this one? Methane. Can we do part of it? It's Freon. Is there any part of it we can do?
That's freon.
Chloride. So that's
Dichloride.
Cl2, Fl2. And do you remember what methane is?
I did it once. I forgot what it was though.
It's a carbon and 4 hydrogens.
That's freon.
Yeah. Oh, wait, maybe that one's wrong. No. Methane should have an H in there. Oh, see, now I'm looking at this and I think I did not do this well, but you know. Okay, lead 2 sulfide. That you can do.
PBS.
There we go. Very good. Ethanol I left there for you. So this is just straight up ethanol. We don't give it some other crazy name. And ethanol is grain alcohol, right? Okay, per, since I totally blanked out on it, refers to a molecule containing an oxygen-oxygen single bond. So hydrogen peroxide, because it has an oxygen-oxygen single bond. Graphite, what's this one? Carbon, easy. Okay, calcium sulfate dihydrate. I bet you can do it.
There's gonna be a calcium.
Ca. Mm-hmm. Sulfate. So we're gonna have what? Yeah. SO something.
And then 2 hydrogen and then another.
So an
two, and then
SO4. SO4 is sulfate.
Okay, so is it always 4 with the oxygen?
If it's S and O, it's always because that's just the way they're going to line up on here.
Okay.
S and O are always going to line up as 4. So it's going to be SO4. And then there's your dihydrate, right? Your 2H2O. All right.
What's hypo again?
Hypo is, okay, so hypo, I don't know what they mean in this case.
Under.
Hypo typically means under or lower. Yeah.
No.
So what is this first part? We can do the first part. Disodium. There you go. Thio. So it's a thio. Do you remember where thio came in?
Hypo.
Thio is when you involve, it's when this weird sulfur thing gets involved. So don't worry about it yet. We're just doing these because they're interesting. How about this one?
Nitrous oxide.
Right, but what is it? You were saying it. Dinitrogen. Yep, it's exactly right. Good. Okay, calcium oxide. What would that be?
CaO.
Look at you guys. You're good. All right. All right. How about this one?
Calcium carbonate.
Yes, it's calcium carbonate. Good, good, good. You got it. You got it. You got it. Okay. See, we're getting there. We're getting there. All right. So here's your Lewis dot structure for nitrogen. Okay, I'm going to remind you how to do the Lewis dot structures. They're easy, right?
Sorry.
For nitrogen, we have 5 valence electrons, so we can put the
When you
N in
start
the
putting
center
all of them
to
together,
represent
you need to be sure you can do
nitrogen,
one.
with 5 dots around it. Those represent the valence electrons. Remember, valence electrons are the electrons that are involved in forming chemical bonds with other elements. That's why they're so important in chemistry. We can find the number of valence electrons using the periodic table. The group number tells us the number of valence electrons for the element. For example, hydrogen has 1 valence electron because it's in group 1, sometimes called 1A. If you look at group 2 or 2A, you'll see that those elements have 2 valence electrons.
Yes, we know.
We'll skip over the transition metals since they're a bit more complicated and probably don't apply. We'll go to 13 or 3A, which have 3 valence electrons. Then 14 or 4A, each of those elements in group 14 or 4A have 4 valence electrons, all the way up to group 18 or 8A, which have 8 valence electrons. Nitrogen, which is in group 15 or 5A, has 5 valence electrons. So to draw the Lewis dot structure for nitrogen, we'll put the N with 5 valence electrons around it. So that's the Lewis dot structure for nitrogen.
So once you get doing that, you start putting them together and you can make the molecular structures. So what do you suppose goes here? Another word for a lone pair.
Single. Or
So we're looking for, go away, go away. Oh my gracious, go away. No, it won't even go away. Unshared is what we're looking for, but it doesn't want to go.
oh,
Man,
unshared error.
stuff's gonna make me crazy if it doesn't work.
You wrote it down.
So your unshared pair,
Unshared.
and then I want to do, oh my gosh, y'all.
What?
I made a mess of this. So when 2 chlorine atoms form a covalent bond, each atom contributes 1 electron to a shared pair. So how many does chlorine typically have?
7.
Right, 7. So if you look here, where they both are in the middle, this is your shared pair. That means they now both have 8 because they started with 7. Okay, are we following that? Yes, all right. So an unshared pair or a lone pair is a non-bonding pair. So if we go here, I wonder if this will actually work if I put it back where it goes. Might not. So a And it won't because my life is trash today. All right. Single bond is a covalent bond in which two atoms share one pair. The electrons can pair in any order. However, any unpaired electrons are usually filled in to show that they will form a covalent bond. So this dash represents one pair, correct? If you look here, this guy had one and this guy had one lone electron. And now there's this line represents the pair, right? Okay. And then this just shows your number of electrons and your number of bonds that typically go with elements in these groups. Now your Lewis dot structure, this is supposed to be a sample problem, but it's not gonna let me do it right because it's gonna be stupid. Maybe it will. So draw CH3I and it won't let me. See, we were supposed to do this like a thing. So here's your, I'll do it this way. Here's your C, H, 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 and your I. The way they end up pairing up is around this guy in the center because each of these H's need one more to make a pair, right? So you're gonna take this dude and he's gonna go here. This one will go here and this one will go here. And this guy also needs one more to make a pair. So he'll go on the other side, which means that your structure ends up looking like this. Does everybody understand how that happens? Okay. All right, so then let's look at the notes for this first part. All right, now these are supposed to appear and disappear. Goodness knows. Okay, maybe they will. Go. Oh, come on. Now it'll do it. All right, so how does a covalent bond form between two atoms? By sharing. Okay, excellent. And it isn't going to show it, but all right. Oh, there it goes. All right, that's weird. All right, why is the H2 molecule more stable than two separate hydrogens?
Because each atom has a shared pair of electrons.
There you go. So it wants two to fill its outer valence so that it'll be more like a noble gas and be nice and stable. The only way that's going to happen is it's going to pair with another one. All right, explain why the stability described in item 2 does or does not hold true for most covalent bonds. Who has an answer for that? Anybody besides Abby or just Abby? You have something, Cole?
No, not that one.
Okay, what do you have, Abby?
It does hold true except for noble gases. Unbonded atoms have high potential energy, which is released when they form a compound. Bonding causes a decrease in energy.
Yeah, that's a good answer. So yes, your molecules are going to be stable when they achieve noble gas configuration with an outer shell of 8. So hydrogen is going to be the exception because it only has 2 in its outer shell, right? So, all right, this is an easy one. Anybody can answer this. So how does a covalent bond differ from an ionic bond? Cole?
Covalent bonds require less energy to separate and allow for more vibrations, movements than ionic bonds.
Okay, what else? Anything else? Alex?
They're made by sharing electrons, not by one taking the
There you
electron
go.
from another.
Yeah. Yep. So in a covalent bond, atoms share one or more. An ionic bond, atom transfers, right? All right. So then what's a molecular orbital? Cole?
The region of high probability that's occupied by an individual electron as it travels the wave-like motion in three-dimensional space around one of two or more associated nuclei.
There you go. All right, so that's exactly right. Overlapping, or orbitals that are overlapping. A region where there's a high probability. Comment. Check it. Okay, bye. Guys leaving. Bye, guys. All right. So describe the potential energy change that occurs when two hydrogen atoms approach each other and form a covalent bond. Abby, what you got?
The highest potential energy is when they're first, like the level. So when they're first start, they have the highest potential energy. And as they get closer, the potential energy decreases until they're as close as they can get, which is when it's as high. I mean, as low as the energy can get. But if they get any closer,
right,
then they.
That's absolutely right. So you got these two atoms that are going to form a bond, and there's a distance where the attractive and repulsive forces are going to balance. And at that point, it's at its minimum. So right before they balance, though, it's exactly like Abby was saying, lots of energy. So in terms of energy, so here's your hydrogen bond question. In terms of energy, why is the hydrogen bond stable? And I had that answer already up. So now it has an electron configuration like helium, which has relatively low potential energy and high stability. So that's good for hydrogen bond. So why is bond length an average rather than a fixed number? Yeah, Cole?
This is, because chemical bonds don't have a static structure.
Yeah.
There isn't like a baseline for all.
Yeah, so it's like what Abby was saying, the potential energy is going to determine the bond length. Like how close can they get
There isn't a
before?
standard size for all.
Right. Okay, good. So describe your typical physical properties of substances that have, I can't read the question, is it ionic, metallic, and covalent bonds. So let's do this together. Now let's start with ionic. What are our typical, somebody give me something.
Brittle.
Brittle?
Crystal form crystal.
Uh-huh.
High conductors as well.
Yeah.
High boiling.
High melting, high boiling. Great.
High melted eggs.
Great. And they're terrible, they don't conduct anything, terrible conductors in solid form, right? All right, how about metallic?
Low melting points.
Mm-hmm.
Conductive.
Sorry, I just said covalent, sorry.
Okay.
Malleable.
Yep. Malleable, ductile,
Solid conductor.
luster, good conductors. And how about covalent?
Low
Really?
melting points.
There you go.
Anything really,
Yep, low melting points,
anything goes.
not so brittle. Well, no,
It said in the book they had electrical conductivity.
not as much as metallic necessarily. Okay, so there you go. And then hydrogen bond I added at the end there. So check and make sure you got all those. Transfer of electrons, metal to metal. This is the extra definition behind everything we just said. You guys mentioned all of it. So hydrogen bonds are attraction that occurs between hydrogen atoms in a compound. Strongly electronegative, right? So they right together. So what do we get for number 10? Bond what is defined as an average distance between two bonded atoms? Jack? Length. All right, excellent. How about this next one? What is defined by the energy required to break the chemical bond?
Bond energy.
Bond energy. All right. Tendency of an atom to attract bonding electrons to itself when it bonds with another atom is called its
Electronegativity.
There you go. And what is a bond? Oh, sorry. A blank bond is attraction between two atoms, which bonding electrons share equally between, Abby?
Non-polar covalent.
Non-polar covalent. And what's this last one going to be?
Polar covalent.
Polar covalent is attraction where the sharing is not equal. Okay, what kind of molecule? It has one part with a partial charge at one end.
Dipole.
Dipole, right?
Dipole.
All right, and then in general, if the difference in electronegativity between two atoms is between 0 and 0.5, okay, and I'm going to show you that the rest of the world seems to disagree with your book. So you probably got nonpolar, polar covalent, and ionic, right?
Yes.
Okay, the rest of the world is going to tell you that 0.0 to 0.39 is nonpolar covalent, not 0.5. And 0.4 to 0.89 is moderately polar covalent.
0.89
Yeah, can you see them there?
No.
Zero.
Sort of.
0.89,
is moderately covalent.
moderately polar covalent. And then 0.9 to 1.69 would be very polar covalent. And then 1.7 or greater would be ionic. So if you Google this, yeah, you're fine. Which one are you looking at? The third, fourth?
0.9.
0.9 to 1.69, very polar covalent. And then 1.7 or greater is ionic. I don't know why it's different in your book. Could not begin to tell you. Predict the type of bond present between carbon and hydrogen. In polyethylene, what would you predict?
Using the ones that were given in the building.
Mhm.
Yeah.
Did I just read the wrong? Oh, I read 20. I meant to read 19. Predict the type of bond that is present between sodium and fluorine in your drinking water.
Ionic, right?
Yeah, that's going to be.
What?
Do your thing. Yep. All right. Predict the type of bond present between carbon and hydrogen.
Nonpolar.
Yeah, this is actually, it's CH2H4 is what we're looking for. And it has a nonpolar covalent bond.
Wait. What?
20.
Yeah, non-whole. So, yeah, if you use the book, there was a little graph
What is the?
that was super helpful, and you
Yeah.
can kind of go back between the pages, and then, yeah.
What's the difference in electronegativity then? For those two? 'Cause
It's
I-
on that page, isn't it?
I thought one
Find it,
point
it's in the
two has
book.
a difference.
Yeah, what was the, he's looking up the page number for the,
It was,
We have
I
it
remember
too.
now where it was. Just a second. I'm almost there.
you can probably find it faster than I can.
Uh,
My book has more pages in it. 1, 6.
It wasn't in the section, in fact, okay, fine. One second.
Right here. My book has like a gazillion extra pages in it. Right, here we go.
Here it is.
Okay.
195.
Oh, did I just pass it? Oh, I don't have no 195,
That's these
194.
two here.
Oh, yeah, okay, yeah.
That's it.
Yeah, okay. I was looking at here. So, yeah,
So then for carbon, it would be 1.0, right?
This is
2.6.
That might be something.
There you go.
Yeah, you're looking at CA, that's calcium.
Oh, that's what it was. There you go. That makes sense now. Okay. So predict the type of bond present between carbon and sulfur and vulcanized rubber.
Oh, that's a non-polar. Yeah.
Non-polar covalent. Carbon is 2.6 and sulfur is 2.6.
You gotta add the two together. That's what it
No,
was,
isn't
yeah.
it the difference though?
Oh,
It
that's
should
right.
be 0.
Yeah, wait, which one are we on again?
It's carbon and sulfur, which are both 2.6, so the difference would be 0, so that
Yeah,
makes
yeah,
it
yeah,
non-polar.
I didn't mean atom, but yeah.
Sorry, really quick.
Yeah.
On 20, it's 2.6 and the hydrogen is 2.2, so the difference would be 0.4.
2.6 and 2.2.
So the difference.
But look at how many there are. There's 2 carbons, so 2.6 plus 2.6, which is 5.2.
Where?
So so polyethylene is C2H4.
Oh, I didn't know.
That's the tricky part. So it's C2H4. So when you make your H4, you get 8.8, and your C2 would be what, 5.2? 8.8, 5.2.
So then that makes the difference
8.8.
far greater, which would make it ionic. It would be more than 3, which would make it ionic.
But you're doing, it's 5.2 minus 8.8. Right? So 5.2 minus 8.8, I'm not going to try that without my calculator. Is
So
going,
So it's in the negative.
it's a negative number. Whoops. Let me look at it, Abby, when we're done. I want to make sure I get that answer for you so it makes sense, but I also want to get through all the rest of them too. So, you okay? All right, so predict the type of bond present between carbon and fluorine.
Polar.
Here we go. And how about,
Polar is the last one.
and polar, covalent. Okay. I want to make sure we get through all these, so. All right, an electron in the outermost energy level of an atom that can participate in bonding is what kind?
Balance.
Valence electrons. All right, and a structure in which atomic symbols represent nuclei and inner shell electrons. What kind of structure was this?
Lewis. Ozzy
There you go. All right,
Ozzy.
and a possible Lewis structure of a molecule for which more than one Lewis structure can be written. What do we call those?
Resonance.
That's good, right. Covalent bond in which 2 atoms share 2 pairs of electrons. Double, and if they share 3 pairs, triple. And a bond in which 2 atoms share 1 pair is a single. And a non-bonding pair of electrons in the valence shell of an atom is called unshared. Good. All right, now these are the work ones again. So methanol, whoop, I actually bumped it too early. Methanol CH3O3. So this is what methanol looks like. I'm gonna make this bigger. So let me blow up the, oops, blow up this page for you.
Bottom right.
Yeah, I'm trying to make it a little bigger. Oopsie. Come here. No, 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 no. Hey, you. No, wrong way. I got this bar with people's faces down here in the way too. So, all right, here we go. There we go. Do you have something like this?
Yes.
Good. That's what you need. And for propane, it should be right here.
Can you go back to the first one?
Yep, I'll make them both a little bit.
Yeah, I got that first one.
Yeah, go there. Wait, go. I'm
Yeah.
trying to get back. Sorry, it didn't want to move. I'm like, come on. All right. And there is your propane.
What is the total electrons for propane?
So the first one,
For propane,
pro-
120.
2, 4, 6, 8, 10, 12, 14, 16, 18, 20, I think.
Yep, 20.
Your system's on.
No, it's a.
But if you look at propane and compare it to, oh, we don't have the methane up here anymore. I was gonna say, whoops. All right, so there's your Lewis dot structure for water.
I got a little different with that.
I got mine's bent.
Yes.
It's bent if you draw it with geometry. This is without geometry.
Am I go circle, line, line?
If you draw it with the geometry, then it's bent, correct. But if you're drawing just straight up dot, it comes out this way. So when you add if you were to draw the lines instead of the dots, you absolutely would get the bent. And you could draw a line for like right here and right here, you would draw 2 lines and
Yeah.
yes, they would be bent like that.
Is that 3 or 4 lines? It's 3, right?
3.
That's the way I had.
Yep. Do we have 3? And then
Nice.
nitrile fluoride.
That one had a double pair. I think.
Yeah, it can go either way.
I had different. Maybe. Actually,
You got a double bond. You have 1 double bond, 1 single, or 2 singles. Sorry.
I just did all dots and not lines.
Oh, okay. That's fine too. As long as your dots show the same thing that those lines show, then you're right.
Yeah.
This would be with geometry, as opposed to the first one, which was without geometry.
I have
You have what in the middle, fluorine? So, so nitrogen has 5, right? Fluorine has 7. So fluorine has 7, right? Yes. It can't be in the middle because it doesn't have enough free spaces for everybody else.
Okay.
Because it only has room for 1 spot.
All right.
And then we got this here. I tried to find nice pictures to put in here. I wasn't going to try and make a mess of it, but this one's messy. So that's if you did without geometry. Obviously, if you did it with geometry, you'd have a line and a line. Then you're also getting into shapes. So explain the difference, double, single, triple. We've done this multiple times, so I think we know what it is. Why won't you go? Why won't you go? Okay, you're being fun and weird. That's excellent. God, the world is out to get me today. So then, let's look at this one.
Oh, wait, 9.2
Yeah.
is TWO, not
Where?
not here, 14. The difference
Did I
between
say
single
that?
and one triple. 2 pairs of electrons.
2 atoms, 2. Yup, right there. Bingo, girl. That's 1 for each class today. Y'all are doing good.
How many are we up to?
I'll have to look. I don't remember.
I'm pretty sure
Okay,
that-
so Vesper theory is going to predict shape. We've been over that. So this is draw Lewis dot structure and then use it to predict shape. So CH4, that's methane.
See if I was that good of a drawer, I would have.
Yep, it's a tetrahedron. So if you think about this, how many free space, what number, sorry, Carbon has how many in its valence?
4.
Yep. And then each hydrogen has 1. So this is really the only way it can go, right? All right, now with the carbon, oh Lordy, stand up. Carbon having 4 again, and then chlorine has what? 7. Hey. So how are we gonna do? I give up. Oh well. No, you don't need to be Vanna White today. So how are we gonna do that? We're gonna do it like
I don't get that reference.
so.
Like, so we can go across.
So you have double bonds here,
Okay.
or no, single bonds here. Single, 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 single,
Yeah. that's what I know.
and then you're gonna get this tetrahedron here again. Same kind of deal. Does everybody have something like that, or close to that? Yep.
Okay. I have a question on this question.
Yeah.
And it gets extra units.
For nitrogen, okay. So you're getting an extra valence electron. So where are you putting your extra valence?
I have.
Not that, okay. So oxygen has, oh goodness, this thing should stand up. Oxygen has 6. Nitrogen has 5. How many oxygens do we have? 2. So we know it's not an oxygen in the middle, right? That wouldn't make the slightest bit of sense. So we have our nitrogen in the middle. It has 5. It needs 3, right?
Yeah.
And the oxygens have 6, right? So what ends up happening is if we look here,
So nitrogen stays with 7, it's not.
nitrogen,
Charge it?
yeah, so here's 1 for nitrogen, 2, 3, 4, 5,
6, 7.
right, 6, 7, and then it's positive because it's lacking 1. Oh, so what you were having was 1 less? Was that what you mean?
Yes.
Yeah, that's right.
So.
So this
I
is,
didn't realize we could charge. that.
yes, they are, the ones that I'm testing you are not this tricky. So how does one unbonded pair of electrons affect the shape of a molecule? Yeah, what you got?
It bends the atom by putting the shape, it can change the atom.
Right, because they're repelling. So they're pushing away from each other, which causes it to bend. How do multiple unbonded pairs of electrons affect the shape of a molecule? What do you? So one unbonded pair is going to cause it to bend. How are multiple unbonded pairs going to affect it? They're going to repel each other as well as bonded pairs. So they're going to repel other unbonded electrons and bonded electrons. So you get a bent shape again as well. This is when you start getting into funky shapes. So what evidence is there to support the idea that opposite polar ends of molecules attract each other? Did anybody come up with anything for that?
I just put opposites attract.
Yeah, this one was tricky. The book answer that I found was the energy required to separate polar molecules is greater than that needed to separate nonpolar molecules. So that makes sense. That makes sense, but I wasn't sure how you were supposed to know that was exactly what you were going for there. How do polarity and shape of molecules relate to properties of a substance? This is a good one. Yeah.
Non-polar molecules have weak attractive forces. And shape affects polarity, which can give it net positive or negative charges. And then shape and polarity. In the book, it said they talk about like later.
Yeah.
All the different things.
Yeah.
I just put it affects a lot. I don't know what
It does. Like one in particular is taste. Isn't that weird? So shape and polarity affect the way it fits into other structures and how it tastes, as well as its ease of separation and its attraction to positive and negatively charged objects. So interesting when you think about it, your taste goes all the way down to the shape of your molecule. That's kind of funky, but hey.
Taste.
So here's your nomenclature flow chart again, right? This is just another version of the same one you have in your binder that you can always use. You can whip that out for tests too. I'm fine with that. I said that before. That's the flow chart. That's the way that goes. So I was going to show you in the other crazy slideshow that was with the book stuff. I had embedded some what I thought were decent videos, and I thought some of them were worth looking at, like the one on resonance was interesting. The dude was a little dry, but it's funny because it's like a straight up 1960s educational video for real. It's funny because I was like, wow, where'd this come from? Let me find that. I laughed at it, but I was like, this is perfect. It really covers, it explains it, but it's, here it is. Now, will it play is the question. No, let's see, it's not because it's going to be dumb. But YouTube will play it. I'll find it.
Right through the flesh, the bone, the flesh, the skin on the other side, the wall behind you, the 3 people behind you.
Too many things going on one time.
Like, oh, no one's told me to stop. I'll just take this and work, you know? Yeah, it was
There we go. Where's my great 19? Here it is. I love this. This is a throwback.
If we can show
But
that
it's great.
molecules also have natural frequencies of vibration and can understand how light waves interact with
Look at this dude, man.
then we can see
He looks like one of my
why
high school
a molecule
teachers.
will absorb infrared radiation
He really does.
only at certain frequencies.
This could have been Mr. Bauer before his hair went white. I mean, it's the same thing.
If the frequency of the light wave is the same as the natural frequency of vibration of the molecule,
Really
then there
Isn't
is
it?
synchronization. The molecule will absorb energy from the light wave, and the molecule will vibrate.
This
more
guy
and
taught
more
Mr. Wizard. That's
Now,
how
the
old
way
this
in
is.
which the light wave lays hands on the molecule has to do with the fact that the light wave is accompanied by an oscillating
Professor Dave's
electrical
great
field,
grandpa.
while the molecule has different electrical charges on its different elements. The left to right electrical field will push the positive atoms a little to the right, negative atoms a little to the left, and the right to left electrical field will do just the reverse.
Look at this
We can
thing.
reproduce this condition
I want to
by
build
using
it.
an electrical generator to charge 2 condenser
I wish I
plates.
did this as my revolver
With one
Yeah.
charge positively and the other negatively, we can switch the charges back and forth and simulate the oscillating electrical effect of a light wave. To model the hydrogen chloride molecule, we can use 2 lightweight spheres connected by a spring.
What are they made of? Look like tape. Look like masking tape on styrofoam.
Represent 1 hydrogen atom and 1 chlorine atom held together by a
Yep.
bond. The spring rather accurately represents the bond.
Rather accurately. See, because it's flexible.
And
We
rather,
have put a positive charge on the hydrogen and a negative charge on the chlorine. With this motor, we can switch the charge on the condenser plates back and forth, and we can observe the effect of the oscillating electrical field on our model of a molecule.
I seriously
We start
want
the
this toy.
system at rest
This is
and
fun.
slowly increase the frequency of the oscillating electrical field, so that in effect we scan the spectrum of different frequencies. At first, there is no interaction between the field and the 2 charged spheres, but when we reach a certain
Building up.
frequency, which corresponds with the characteristic frequency of our mechanical model, we see that the model begins to vibrate.
Every time I hear like a video from like the 60s, 70s back, I always think like they're audio vibrators.
Yeah.
The voices are amazing.
Oh yeah, they all talk
voice
the
is
same
always the
way.
same. It's always that same
Yeah,
voice.
yeah, it is the same
Same
voice. And all the female actresses had the same voices until like 1970 something. I don't know what that was about either.
As you can see here.
Way to go!
Come on.
Its vibrational
That's fun! I want to build this machine just for fun.
electrical field.
This
Woo!
would totally be allowed. I'm
Or slash
sorry.
and pop.
Oh,
We'll
we're gonna
slow this
animate it.
down a moment to compare it with a molecule interacting with the oscillating electrical field of a light wave. They will interact strongly when the frequency of the light wave is the same as the natural frequency of the molecule. But if we increase the frequency still more so that we exceed the characteristic frequency of the system, we find that again, there is no interaction. The energy of the wave is not absorbed.
This is just like the thing you see when they do the sand, the vibrating sand on the table, and it changes shape and comes to a point where it doesn't move and then it does move. Same kind of
In the case
thing.
of a real molecule, its energy wouldn't change. Now we've seen how a diatomic molecule produces its typical infrared vibrational spectrum.
We get it.
Let's go on and consider what happens.
So this is like, have you ever seen, I want one, I want to build one. Have you ever seen the things that people build with the, it's like bowling balls and they're on ropes of different lengths?
Oh, yeah.
And you let them swing and they do this crazy thing where you can see how it's a wave. Have you seen that?
I keep seeing science teachers do that. And
I
then
want to build
they're
one.
stupid or a kid is stupid and one of them walks in front of the ball.
Why would you do that? It's the same idea.
They'll stand on
I'll
either.
be the student.
Well, the thing is,
You
they'll
would
stand on
be.
either end and they'll think they're a safe distance enough and then it'll just hit them.
It's like,
And
I just
generally,
want to see what
it's
it looks
not
like
in
from
a
the
nice
front
spot
side.
to
It's
live,
totally
too,
safe
so.
distance. No, I'll be the guy standing in front of it.
I'm
Alex is
trying to remember what
he's a
it's
safe
called.
distance away. I'll just push it.
I have an
I'll be-
unpopular opinion.
Whoops.
I think that model, those little wires coming out, I think they had like fishing lines.
Large
above them.
balls on
I don't
the
think they were
other
actually
side.
floating.
I'll find it. These.
Yeah.
It's an unpopular.
I
opinion,
serious. This
think.
one right here this is what I want to build. It's a pendulum thing, but it's a wave. That's why I couldn't put pendulum wave together in my head for whatever
My
reason.
mom texted me like 15 minutes ago out here. It's like, okay, well, this is amazing.
This is fun, man. Come on, load the video. What's the deal?
It's paused.
It shouldn't be
It
paused.
wasn't originally.
I want to build
Okay,
this.
I'm gonna be the kid. I'm just going to stand to the left of the.
Oh no, I was talking about this. I think it's a pendulum in general.
See, they're hitting the little, see how they hit the little things at the bottom? The little tubes. So they're making a noise too, which is really pretty.
Imagine
But watch the way
watching
the wave
woods and
changes
hearing
shape.
that. That'd be creepy.
Like the wave, you'll see the wave.
Like
This is exactly how resonance works. It's the same concept. But you'll watch the wave will change shape multiple times. It'll come back together, it'll go apart.
Right now, it just looks like everything's scattered.
Yeah, but watch how it suddenly evens out. It's mesmerizing. If I had one, I would use it all the time.
Oh yeah.
Look.
You can see it starting to go again.
I mean,
Weird.
what the hey? Look at that.
I mean, holy crap.
I love that.
Just focus on a row of them and don't move your eyes, and it's weird.
Look at that.
There's like 3 of them going right now.
Mm-hmm.
Yeah.
Now they're a bit more jumbled up.
It's mesmerizing. Look at that. Look
One
at
of the
that.
kids-
Look.
The kids are so quiet.
One
They're
of the
like,
kids
That's the
yells,
quietest
"First
those kids have ever been.
one."
I guarantee you.
And we say that. And
Look.
look at that. Wow.
I seriously want to build one.
That's like.
Wouldn't this be fun?
absolutely insane. I mean, right, you got a yard that we
Yeah.
can do it in.
I know. I was gonna say I have a big enough yard. We could make it work.
One of the kids just yells, "First one to the other side."
Yeah.
The
Run.
American Ninja Warrior guys is like, why not? It's the worst.
It's like, but that's how it feels. Like if you're playing on the playground and somebody's on the swing and you try to
That's
run across the
exactly what
swing,
we
that's what it
did.
feels like.
Look at that. Look.
That's what me and my friend did. We would like swing the swings really fast. Like, okay, it's an obstacle course. We would always.
Well, we
get
do
hit
it when
in the head.
kids were on it, and it would hurt at both people if you got hit. So.
I could watch that all day.
See, I want to watch this all day.
It's mesmerizing.
I'm currently watching this other one. Okay, so basically what we need to do when we all get home, this is our homework. We don't need the weekly questions, we just need to watch this.
Look at that. Look.
Build the length of the screen. Just so that they start lining
That's
up.
me, except double the size.
Now look at them. They're in bunches. Look, 2s and 3s, 4s and 5s. That's nuts.
Yeah, now imagine what would happen if it were twice the size. Whoa, now it's all right back together. The kids are so quiet. I'm like, they have to have been threatened to stay quiet. I would just be like, wow.
Just when you think it's done, it's not done. I mean, for
They
real,
really
man.
slowed down now, but they're all in a row again.
That's just wild.
Can we watch that again?
Right.
No,
So,
I think we need it
anyway,
one more time.
That's your idea. This week's test is a short test, Nah, there's one that's light up. That's cool. This week's test is a short test and it's not crazy difficult. Y'all will do fine. I'm not worried about that. As long as you guys are doing your work, you're doing okay. Progress reports are gonna go out to probably tomorrow. I want to make sure I get everything in and it's finalized and it looks nice. I have a meeting tonight. Oh, there's our caramel sauce. I have a meeting tonight, so I want to make sure that I do them nicely and I don't rush them. So if anybody has any questions before you take your test or whatever, let me know. I'd love to be able to get your test on this progress report, but it probably won't. Okay, are y'all good? Yes? All right, well then my folks over here. Good.